we're going to discuss the post-processing of a project on Lakshman file. Okay, so let's go through it. This is the file which has got solved. Okay, so we have this all 4 cases over here. That's the PPT. We'll just try to work on it. Okay, so if you can see this here, guys, Jai Bharat is here.
Yes, I'm here, sir. I was working on that parallelly. No problem. I'm here, sir.
Okay, keep watching it here. So the total deformation that we having here is, so you have to click on this total deformation. Once you click, see this, it's coming in the elements are showing. So what we need to do is, and there's a maximum minimum button, just click this, just hide it for a minute. Then you have to go to the results. Everybody please look at here, just hold your all work whatever you're doing. So just go to the result tab and just click here, say no wireframe. See, no wireframe means your elements gone, and if you want element you can say show elements. Okay, this is the one thing which we use majorly, so that's why I'm telling you. Okay, so this is our con rod. Okay, you have to keep it in isometric view. Look at this, it's an isometric view. Okay, this proper view, your mouse middle button, and then make it a proper view over here. The next thing is this is we call legend or contour. So now you can see we are having 0.00. It means after decimal we are having many terms, right? So what we need to do, just click and then say digit and say 2. Okay, what you need to click digits and say 2. So at least you should have minimum, like it is not should go many digits, right, after decimals. So that's you need to do first digits 2, 3, whatever depends, right? Now second thing is, in case, because we already have hidden this time and date in your software, it might come. So you just need to again, where you need to click on this, the something which is written here, right, this all total deformation unit is written. You have to click your right button, mouse right button, and then it will appear, and just click once again here, mouse left button, to hide this date and all. So this is a color combination, your contour plots, right? Now you can see it will represent like 0 to max, right? So 0 indicates in a blue color, and then slightly you see the color is changing as well as the value going up, right? So what is how you need to understand first that what we apply we are getting same or not, right? That is the first important question is we should ask ourselves, right? So if you look at here, this is called true scale, right? Whenever you take any photo, let's say I wanted to take a photo of this, so I will keep like this. And sorry, you just copy this and paste here. So this is the photo. Okay, so the maximum deformation, this is how you need to keep. Okay, and second thing is, just keep always very near to your this legend, little gap. Don't take a complete photo of this also, like you like this, it is not right. Just take this photo with the same, this is we call triad, right? Just take a photo like this, triad, and then say paste, and here put this, or some people will put here also. Okay, so it's up to you. And then just click one, then click second, select it both with your control button, right click, group, make it group. Okay, so this is what we expect. Okay, now what is the total deformation you have observed on your piston pin? Okay, so the deformation value is 0.096 mm, correct? Now do one more thing. Overall deformation plot for assembly. Okay, here You should be good in PPT also, okay, because that's your output. So you have to go to the home and say time. Here you can say adjusting material C70 S6 steel. Okay. Same thing you have to do here. Propose material. ALI, right? Clear, everybody? This thing is clear?
Yes. Yes.
So make sure.
Yes, sir.
That's great. Thank you. So make sure like you should keep this view always in true scale. Whenever you take photo for your PPT, always take it in a true scale. Okay. See, now you have to check on the deformation always the two things. First thing is, since the design was symmetric, right? So just right click view, front view, check. If you make it undeformed, see this. So your result should be same. See this. If you take it cut off it, see whatever contour. Then look at this is complete blue, complete blue. Little patch over here. Look at this. There is a little patch over here also. Right. So you should have the same pattern. See this symmetric pattern. If you are not having symmetric pattern in your results and your design is symmetric, okay, but you are not having symmetric pattern, then your results are wrong. All the way whatever value you are getting, it is behaving properly, everything is okay, but results are not showing symmetric, then it is not acceptable. Why? Because you have to check that's like why it is and what is the problem. If it is design is symmetric and you are not having contour, this is we call contour, color contour, not symmetric. It is because of you might have defined wrong contact. You have maybe selected unnecessary surface here or extra surface, at one side and another side. So this might happen, right? So it might be because of your modeling error. So but you should not accept this. You have to check why it is not having symmetric. Okay, so that just check that location. Second one is not applying load symmetrically. The load direction, the load is also, if the load is not symmetrically, then where the load is more, it will shows more contour there, and where the load is less, it will show the less contour there, right? So you have to check the load also. You have to check your constraint also, whether constraints are fully symmetric or not, right? Right, you are constraining, let's say all degree of freedom here, and you are considering only 2-3 degree of freedom. So again, it obviously it goes stress here, stress less here, so it shows asymmetric. So you have to check. But in case your everything is perfect, then if you are not getting like this, then something wrong with your context. Getting it? Jai Bharat, Lakshman, Ram.
Yes, sir. Yes, sir. Yes.
Okay, this is the one sanitary check we do always. So that's very highly important. That's a deformation. Now, the second thing is you have to animate this. Okay, animate. So second thing is we have to animate. So how to animate this? Just keep some little exaggeration view, because when you animate this without exaggeration, you can't see like what happening, right? To feel good, to understand what happening, we animate. But make sure, because this plot, let's say your client is sitting in front of you, or he's in Microsoft meeting, or he's also looking at your screen, then in front of him, don't do this thing like taking very high value. So you have to use your judgment. Okay, just keep it like a value which should be not look like unrealistic. Also you can explain him also, right? This is for explanation purpose only. So just click on the animation tab. See this. So let's zoom to this first. What we did is we have applied pre-tension on the, look at this, it's getting little, it is trying to creating a tension here. See the bolt, right? It is visible. Everybody see, look at here by your eye, see this, it's getting tension. Everyone.
Yes,
Yes.
yes.
So,
But it seems like it is pushing the connecting rat, right?
so it should push now. You are applying
Yeah.
tensioning there. You are what you're doing is creating tension now. So it should push.
Yeah. So it should compress the connecting rat.
Yes, let me. I'm just exaggerating a little more. Okay, now you can see. I just little exaggerated more. 25% of load, 50%, then 75%, and 100%. See this. Now see this. Getting down, it getting compressing. See the compress at both end. So it means our P tension acting properly, right? You should have this behavior. Okay, if you are not having this behavior, then your P tension is not working properly. So you can see the P tension is created. It's creating tension, in the joint also, here also. So you might see some stresses to the whole wristed. Okay, here either bolt dia, this outer is supposed to be decreased. It is not properly designed. If you can look at here properly, see this. Some of the part of the bolt head is going out, right? This much. So that's the one thing. Second thing is you see some kind of stresses here also. These are some compression in nature because of bolt P assembly load. Now this is the first step. It is showing down, right? The second, go to the second. See this. What happening? It's going up. Up means what load you applied? You have applied tensor, means you apply on the bottom pressure, right? So it should take up. See this, it's taking up, right? So we have to check like the way that we have applied the thing, like your loads, it should behave in that way. Now look at the boundary condition. So what boundary condition is saying? You constraint here. So you can see you are having minimum deformation at the location of constraint, right? 0. And which the part which is very away from your constraint or a free part. See this con rod, it is having max deformation. This is also the sanitary check. Clear to everyone? Sanitary checks are clear. First for a con rod. So con rod we are having around this much deformation. So please, since we are interested in the con rod, so take a separate photo of con rod also. So our interest is con rod, so you have to take a separate photo. Okay, if you wish, you wanted to keep this triad coordinates, you can keep. Otherwise, you already have shown in the assembly, so not issue. Always make it small, huh? Don't make it bigger on this thing. Okay, so the next thing is, now if you even animate this, you will see this portion, because you are leaving now pin, right? So obviously that it will get transferred to the air because it's connected, right? If you look at here, see this, the deformation is high here, correct? Obviously, when you remove this two part, only keep this. So this deformation transfer to here, right? I mean slowly decrease. So what is the value here is around this color, right? 0.032. Look at this, same you got it here. Correct? Getting it? Can you see this, right?
Yes.
Same you are having here also. When you just hide this all parts, only keep that part. So this is how you can see, right? So we are interested in the best product. Now look at this. What is the yield we are having is 550, correct? So already max value is 543, but again that is the localized. Okay, that is the localized, correct? Look at this. If you have to click on maximum first, you see this at the corner. Correct. See all band coming to the corner. So we need to understand what is localized. Okay, so let me come to that in a minute. Now, what we suggest is, because since 550 is very less, right? You are at 548, right? So there is no meaning. You can play with this button just to have proper contour, just to explain the client, like I am having some kind of a good contour band, right? So let's say I'm just putting 250, see this. So I can see some contour here also, right? I can see some sort of contour here. Otherwise, if I keep this as it is, then it looks everywhere blue, right? So that's not good, right? So you can make it like this. See, you are having contour here. This sort of only one row of elements got, red, that we can discuss. See, you are having contour here also, right? So you have to make it like this. All the way it is passed, but let's see. So first you have to take a photo. Just take a first symmetric photo, I mean your isometric photo, like this. This is one my stress plot, okay? After you keeping this photo, paste it here. To make it, this photos are very small. Okay, and then go to here, insert, and just create a one. Okay. Oh, sorry. Now zoom to this area. Click on maximum so that you can zoom only the area which is showing maximum. Now see this, you have to make it like this. Now uncheck this now. Keep it the view so that person can understand, by looking to a PPT. Right, so it is visible properly. Now, you have to switch on now elements. This is called, zoom view, right? The area where you are having high stress, zoom view. Okay. So now if you can see here, first thing is you have to take a photo. Make sure this should not pass, like proper professional photo. Self-explanatory photo, okay? Then paste it. Okay, now let's see, we will do that. So now you can see this, it is showing here, right? Max, Lakshman and everyone. There is a tab called Pro. Everybody is here with me? I just wanted to hear 3 yes.
Yes, sir.
Yes.
Jai Bharat?
Yes, sir.
Great. So now one node to another node and maybe just a 1 mm, right? So this looks something fishy. This looks something not realistic. This looks something artificial, okay? So that's why we call this as a artificially numerically generated stress by the tool, and because of the calculation at the corner, at this corner node, what will happen if you go for the sigma equals to P by A. So at this corner nodes, because calculation done on the nodes, so at this corner node stresses, the area becomes very down, right? Very less. So when the area become very dense, right? So the stress will increase high, okay? Even at the same load. As you keep on going for a very fine mesh, your stress going up, right? This is what is a concept. So this is, some people call singularity, some people call stress singularity, artificial stresses, local stresses. We call localized stresses or artificial stresses in ANSYS point of view. Some people maybe call it a singularity, okay? Always show the, even the your arrow location at the right place, you know. You should not, like if you are getting a stress here, you're showing a arrow here, it is again wrong, you know. So sometimes customer checks with your file, so it is recommended to do that one also very properly. 223.05, right? So this is how you need to show. Now this is clear, everybody?
Yes, sir. It's clear, sir.
Share, clear to you?
Yes, sir.
Now coming to the another here, you can see here we are having thing, then you explain, sir, it is not visible in. Then if you give an answer like an engineering point of view, just in a 1 mm length, you see the difference. Now we always check the, you know, symmetric part. We always check the some numerically relation between the stress point over here. So this looks pretty fine, you know, like after the this corner nodes, we can have a uniform stress distribution. The values are also seems promising, so that's why we are keeping that, right? So this way you need to explain in case if any question arise, right? Shreya, I think Shreya, you also do this thing.
Yes, sir.